introduction, and also hello from my side. And I'm excited to talk to you today and present our paper on benchmarking serverless workflows. And to motivate what serverless workflows are, let us first look into serverless functions and how to use an application with them. Where we have our serverless function in the cloud, in this example, book hotel, where we just have to ship the function code and then can invocate it from a lot of different sources like IoT devices, from a web application, or the user invokes it themselves. And when they do, they send over some invocation payload like the trip details for the booking and get back the booking ID. However, usually that's not your complete vacation just in a hotel. You may also want to book a rental. So when you do so, you need to invoke a second function because they're usually very short-lived and have very encapsulated functionality. You then need to send again your trip details, maybe your booking ID of the hotel to connect the bookings, and then get back the rental ID. And the same is true if you also want to be there and book a flight. Which may become tedious and hard to coordinate. So the cloud's advanced and now offer a workflow orchestration where you can build larger applications with by coordinating these single serverless functions. So you just have to send the trip details to this workflow orchestration, and they then take care of for you on coordinating these functions, and then you just get back the results of your booking in the end. So this is nice. These workflow orchestrations automate the execution of functions through using control and data dependencies. So you just have to give them your function code and the orchestration specification, and they'll take care of the rest of you. And this also comes with some other advantages of the serverless paradigm, such as infinite scaling, pay-as-you-go billing, so you don't have to pay for resources you don't use at the moment, and a very easy deployment, as you don't have to take care of that yourself. So this leads to, of course, more developers using workflows and also more research in optimizing workflow systems. However, when looking at this research, where we evaluated 72 papers on serverless workflows, we found that they use very different benchmarks to evaluate their workflow benchmarks and their applications. More specifically, we can see here we group them into some categories, that there's not a single category used consistently throughout all of the papers. And the same is true for the cloud platforms evaluated, where we can see that there is a big amount of works using AWS for evaluation, and also a lot of research platforms are being used. There is no single platform that is used as a consistent comparison. So the problem is that there is no comparability across these works, as we don't have a benchmark suite that enables comparing them. And it's also not straightforward to build such a benchmark suite, as these workflow platforms are black box systems. So actually, when you port a workflow, the impact on performance and pricing is unclear. And all of these workflow platforms follow different programming models and different implementations of these workflow orchestrations. So it's also not straightforward to port a workflow from one cloud platform to the other. So what we looked at in this work, therefore, is how can we actually model workflows in a platform-agnostic way to then port them to different cloud platforms easily, and how do the different services compare that are offered at the moment. So let me start by the modeling workflows in a platform-agnostic way. More specifically, what we looked at in our work is 3 different cloud platforms, AWS Step Functions and Google Cloud Workflows, which both follow the state machines paradigm, and also Azure Durable Functions, which uses the orchestrator function. And we opted then for modeling workflows with the formalism of Petri nets, which you can see here. We have our example workflow where we're booking our trip, and we model all of the different serverless functions as function transitions. We can also show which data they're reading and writing, and we also extended these Petri nets with resource annotations, which enables some formal analysis on them. So the advantage here is in the clearly defined semantics this formalism offers us, and some analysis are enabled by that, such as finding out if a workflow ever terminates. So this is great. We can now model our workflows platform agnostically, and we can now go ahead and transcribe this to the representations of the different platforms. And we also evaluated our model by reviewing the literature on serverless workflows, and could show that we can actually express the workflows used in research at the moment, and that we also don't introduce transcription overheads when transcribing from our platform agnostic representation as compared to natively implementing these workflows. So this is good. We can actually safely go ahead and deploy our workflows to the different providers, and are then able to analyze the performance, scaling, cost, and stability of the workflows and the workflow platforms. But let me first continue by giving you an overview of how we implemented this. So as the paper title may already give away, we're building on the serverless benchmark suite, which is pre-existing. So the serverless benchmark suite actually also has very minimal user involvement. We just have the user, which can then select a benchmark, which for the serverless benchmark suite just consists of a single serverless function and the data used by the function. It then goes ahead and deploys the functions to the cloud selected, uploads the data, and executes the function and collect the timestamps. We can then download the measurement data and actually analyze the measurement data. So now building on this, we extended this to also work for workflows in our work SeBS-Flow, where now our benchmark applications not only consist of a single function, but all of the functions used by the workflow, the data used, but also the orchestration specification, where we say how the functions should be orchestrated. We can then deploy the functions and upload the data building on SeBS, but also deploy the workflow by transcribing it to the respective cloud platform selected. We can then go ahead and execute the workflow, collect timestamps on its execution, also download the measurement data, and are then able to analyze the measurement data. But before we do so, let me first shortly introduce the 6 different benchmark applications we're proposing and also using for our evaluation. I'm showing the names here. So we were aiming for a wide selection of workloads covered. We have some variety in it, such as the trip booking application, which is a bit similar to what I just showed, where you can book your vacation. We also have the video processing benchmark, some ML workload, but also a scientific workload, which is the 1000 genome benchmark. These workflows do not only differ in the workload they're executing, but also in the amount of functions that are executed, spanning from only 4 to 19 different functions. They also encompass different parallelisms from a sequential benchmark to the 1000 genome benchmark with 12 functions executed in parallel. They also have a different length of the critical path and also different amounts of data used, where we can then nicely see how this impacts the performance of the workflow platforms. And if you say this looks rather small scale, that is actually true for most workflow workloads deployed on the workflow platforms. They're usually rather small scale, as different studies and also traces released by the platforms show. So these are actually realistic execution sizes, though all of them are configurable. So we then went ahead and evaluated 5 different research questions related to the performance of the cloud providers, where we looked at the runtime differences, what causes them, how well they support scientific workflows, how the pricing compares, and what the evolution of performance and stability looks like. However, that is, of course, too much to cover for this presentation, so I'll only go into detail in the first 2, and for the rest, you'll have to look at our paper if you're interested. So now let us look at the major runtime differences, where I'm showing here a different plot for each benchmark, and on the x-axis you can see the different cloud platforms, and on the y-axis the duration. And there's several things we can notice here. First, we can see that AWS Step Functions actually is the fastest workflow platform for 3 out of our 6 benchmarks. And while Google isn't the fastest platform for any of the benchmarks, it's also not very much slower than AWS on these benchmarks. For the other 3 benchmarks, Azure Durable Functions actually is the fastest workflow platform, whereas for the other 3 workflows, it is by far the slowest. And we can also see that it exhibits the largest amount of performance variance. So naturally, this made us wonder, what are the causes for these runtime and stability differences? So we looked at the execution time in a bit more detail, and I can illustrate this by using our example workflow again, where we now looked at the critical path of the workflow execution, which means that we're looking at the sum of the maximum function runtime per phase. So this means if we would have 2 book rental functions executing in parallel, we would take the time of the longer running functions and add it to the critical path. And using that, we can then compute the orchestration overhead by subtracting the critical path from the total workflow runtime. So we see how much time is happening in between the function executions caused by the orchestration. So now splitting the runtimes into these 2 components, where we are showing the orchestration overhead as the shaded area on top of the bar plots, we can see actually that these long runtimes on Azure are mostly caused by overhead induced by the workflow orchestration. On the other hand, AWS incurs very less, not a big amount of orchestration overhead. And for Google Cloud, it kind of varies between workflows a bit, how much orchestration overhead is incurred. So clearly we have to look into more detail and find out what are the actual sources of overhead in the benchmarks and what are the reasons for these variations in the critical path. And for the sources of overhead in the paper, we looked into 3 different sources, which is the storage I/O, the return payload, and also the parallel scheduling, where I will now only go into a bit of detail for the parallel scheduling, where we employ the micro benchmark, where we show the relative overhead of n functions, where each function sleeps for t seconds. And here you can see the results on AWS step functions, where we have the duration on the x-axis and the number of functions on the y-axis and the relative overhead annotated in the plot. And what we can see is that while there is some relative overhead for short sleep durations, it kind of fades away the longer we sleep. And it's also not very much impacted by the amount of functions we're scheduling. On Google Cloud, approximately the same is true. While there is a little bit bigger relative overhead for shorter sleep duration, it also kind of fades away for longer sleep durations. However, when we now look at Azure, we can see that the relative overhead incurred is an order of magnitude bigger. It's up to 42, starting from only 8, so it's really a lot bigger than the 1.1 on Google Cloud and 1 on AWS. And it's also not clearly correlated to the number of functions or the sleep duration. So now we can look at how this impacts the scalability of our benchmarks by looking at how many containers are actually spawned on the cloud platforms. For example, for the trip booking benchmark, where we have the execution time on the x-axis and the number of containers invoked by the cloud platform on the y-axis, we can see that Google Cloud, shown in green, and AWS in blue, actually do spawn a lot of containers to accelerate the execution. On Azure, however, we never have more than 3 containers simultaneously, which delays the execution a lot and also means that the workflow takes longer in total. And the same is true for the different benchmarks. For example, here for the machine learning benchmark, we can see the same behavior. Like Google Cloud and AWS both spawn a lot of containers, whereas Azure demonstrates limited scalability in terms of containers. So we can see that a significant part of the overhead on Azure originates from these parallel schedules, but also the storage I/O, which I didn't show now. So looking at the variations in the critical path, then we examined the impact of cold starts and also the impact of OS noise, where I will now only go into detail on the latter, where we estimate the vCPU share by running a very tight loop and then recording when one iteration takes more cycles than expected 5,000 times. And we can see the results here, where we have the memory configuration on the x-axis and the suspension time on the y-axis. We also notice that we do have just a flat line for Azure, as the memory there is not configurable as a user. It's allocated by Azure automatically. And what we can see there is that actually for Azure, for lower memory configurations, the suspension time is lower than for AWS and Google Cloud, which can explain why the critical path on Azure is faster than on these other 2 platforms. And looking at our benchmarks, we can actually see that this has a big impact when we normalize the execution time according to the suspension time. So looking here at Google Cloud and AWS, where the normalized path is shown in blue, we can see that it is, of course, a lot shorter, even though not as short as in Azure. When we look at machine learning benchmark, which uses a bigger memory configuration, we can see that the impact is less pronounced on Google Cloud and AWS, but it is still there. Yes, so we learned here that larger CPU allocations on Azure for these low memory configurations of benchmarks actually can explain the shorter critical path. And also what we showed in the paper is that cold starts are a major factor influencing the duration of the critical path. So now to conclude my talk, what we're proposing is a benchmark suite and a platform agnostic model for serverless workflows. In our evaluation, we showed that our workflow model can express workflows used in research and that there are no noteworthy overheads when transcribing from our representation to the representation of the cloud platforms. We also evaluated the cloud providers regarding the performance and the cost of the proposed benchmark applications. And the benefit here is that we now enable the benchmarking of the same workflow on different platforms and also understanding the behavior of black box cloud systems, therefore establishing comparability between them. And that's it from me. Thank you for listening, and now I'm looking forward to questions, and feel free to check out our paper and artifact and reproduce our results. Thanks.